How does one apply ab initio calculations to determine atomic structure? We'll start by reviewing what we learned from the particle in the box. First of all, energy is separable in Cartesian space. The particle box is solvable in three-dimensional Cartesian space, and the energy, E in the x, the y, and the z direction, are each independently solvable and therefore independent of each other. However, when trying to construct an atom, one realizes electron orbits are not Cartesian. The electron orbits relative to the nucleus, and both are moving through space. Therefore, the quantum solution must be translated from Cartesian absolute coordinates into relative polar coordinates. The three polar coordinates are r, the radial distance, in this case, between the electron and the orbit center; theta, the angle of azimuth, the number of degrees of movement to the left or the right; phi, the angle of elevation, the number of degrees moved up or down. When converting from Cartesian to polar coordinates, you get the following results. X is equal to r sine phi cosine theta. Y is equal to r sine phi sine theta. And z is equal to r cosine phi. By looking at this, one sees a function that is separable in Cartesian space is no longer separable in polar coordinates. For the particle in the box, f of x, y, z could be expressed as f of x times f of y times f of z. However, f of x is now f of r theta and phi. F of y is now also a function of r theta and phi, and f of z is a function of r and phi. This loss of separability has actual implications in the physical universe. We will now look into seeing what those implications are. First of all, the energy in Cartesian space can be solved by solving the Schrödinger equation. The Hamiltonian operating on psi xyz, as you saw, was equal to the energy E sub n in the x direction times psi x plus E sub quantum number ny psi y plus E quantum number nz psi z. In Cartesian coordinates, energy is purely translational. It is quantized in increments of n, and it is separable into independent components. When one translates these results into polar coordinates for a hydrogen atom, the question then arises, what is the solution of the Hamiltonian, of the Schrödinger equation, the Hamiltonian operating now on psi of r theta phi? First of all, the difference is the angular components are degenerate. The wave function psi of r phi theta can only be split into a radial distribution function, r of r, and an angular function, capital theta, of theta and phi. Also, since I have a positive nucleus and a negative electron, there is now a potential energy. So the full Hamiltonian is the kinetic energy minus mh squared over 8 squared over 8 pi squared I times the second derivative of the wave function plus a Coulombic potential minus E squared, where E is the fundamental charge, over 4 pi epsilon 0, where epsilon is the permittivity of free space, times 2 times r, the distance between the electron and the nucleus. The solution to the proper wave function, starting with the result of the radial distribution function r of r. First of all, instead of one solution, there are now a set of solutions for this radial wave function. The potential energy, V, as you saw, since it is coulombic, is a function of R. The solution of R sub R squared dt equaling 1 therefore changes with R, that is the normalization. For each solution, the radial wave function R of R is proportional to 2 times the charge of the nucleus Z times R divided by an integer n over a constant called A. As you saw, the radial distribution function is a function of n, the principal quantum number. A is calculated for each electron in each atom as the mass of the electron over A0 over the mass of the nucleus, where A0 is the Bohr radius, 52.9 picometers. Since the mass of the nucleus is much greater than the mass of the electron, A is therefore essentially equal to A0 over Mn, the Born-Oppenheimer approximation, which lets one calculate the nucleus as being essentially stationary. For each solution, the radial energy is also dependent upon the angular momentum L. This is true because when one is solving the Schrödinger equation, the eigenfunction is E, and kinetic energy, expressed as angular momentum, must balance potential energy for the electron to be bound, in other words, to continue orbiting the nucleus. Individual components of the angular momentum are no longer separable in polar coordinates, so only the total angular momentum can be found. The result of this is that your radial distribution function is a function of the principal quantum number n and the angular momentum quantum number L, a number that you knew existed but now see why. Additionally, also confirming what you already knew, the value of L depends upon the value of n. Therefore, L can have any integer value from 0 up to n minus 1. We now look at the next result, the result for the angular theta of phi theta. As seen, the total angular momentum L is determined from the solution of the radial function R sub R. In converting to polar coordinates, you also saw that Z was equal to R cosine phi. Since Z depends only upon phi, L sub Z, the Z components of the angular momentum, is separable. Since the Z direction is separable, this will always be the reference axis. This is important and will come up later on in spectroscopy. Therefore, the solution to the Schrödinger equation on the angular component of the wave function, the Hamiltonian operating on theta of theta phi, equals E theta phi, equals a normalization function, e to the minus I times some constant m sub Lz over phi times the wave function theta of theta phi. This results, the ab initio calculation of an electron on a hydrogen atom gives the result that theta of R phi theta is equal to a radial distribution function R of R, an angular function theta of theta phi, which is equal to, and those are equal to a function R sub n and L, two quantum numbers, and the angular function theta is now a function of m sub Lz, where n is the principal quantum number. It's the energy level and any positive integer. L, the angular momentum quantum number, gives the orbit. It can have any integer value from 0 up to n minus 1 because in the radial function it depends on n. M sub L, Z, the magnetic quantum number, gives the orbit direction relative to the z-axis. It can have any integer value from negative L to positive L, because being a solution of the angular wave function, it is already dependent upon L. Normalization of these functions. Setting the integral of r sub n theta sub theta phi squared d tau equal to 1 gives the following. A graph of the normalization function is essentially a three-dimensional probability map. A graph of the most probable electron position gives what we commonly call the orbital shape, round for s orbits, dumbbell shaped for p. There is also a small but finite probability the electron could be in the nucleus. Looking at the probability distribution function, there is also a small but finite probability that an electron attached to an atom could be at infinity. Quantum mechanics can certainly get weird. We have seen that with polar coordinates, the wave function can be solved for a hydrogen atom. However, what about other atoms and molecules? First of all, ab initio calculations can only be solved for hydrogen-like atoms. A hydrogen-like atom means any nucleus of any size but with only one electron. Because in this case, the problem is additional electrons add additional potential energies to the Hamiltonian. Wave functions with more than one electron are mathematically unsolvable. Therefore, all of the atoms are approximated by linear combinations of hydrogen-like orbitals. This means addition and subtraction, because these are the linear functions. Therefore, the helium atom, 1s2, will be approximated by the wave function of a hydrogen 1s plus or minus the wave function of a second hydrogen 1s. The combined functions are then renormalized, meaning they are set equal to 1, so the square of h1s plus or minus h1s squared d tau would be set equal to 1 to receive a new normalization constant. Two methods are usually used in the normalization: perturbation and variation. Both make minor systematic changes to constants in order to minimize energy values. The calculated answer cannot be lower than the energy from experimental data, however, because you cannot make a better universe than the one that already exists. Molecules are approximated the same way, by using linear combinations of approximated atomic wave functions. It is important to note, mathematically unsolvable does not mean it is limited by human ability. It means the function itself can never be solved. The amazing part, the approximations used to get around this problem perfectly match physical reality. As mentioned previously, quantum mechanics can get weird. We will now look further and look into molecules and spin, the quantum number which has not been looked at yet. You may recall the Pauli exclusion principle from general chemistry that no two electrons can have the same four quantum numbers. Explicitly, what Pauli said was that a proper wave function must be asymmetric with exchange to variables. To find out what that means, let's try to make H2. As mentioned, the wave function for H2 would be the sum of two hydrogen wave functions. Let's call it hydrogen 1 with electron A plus or minus hydrogen 2 with electron B. However, protons are indistinguishable from other protons, and electrons are indistinguishable from other electrons. Additionally, according to Pauli, this function must be asymmetric with exchange to variables. So you have two possibilities. H1SA1 minus H2SB is asymmetric. A minus B is not the same as B minus A. However, H1SA plus H2SB is symmetric because A plus B equals B plus A. To get around this, let us introduce two quote-unquote dummy variables into the equation, alpha and beta. You now have three possibilities. HA electron alpha plus HB electron beta, HA electron beta plus HB electron alpha, HB electron alpha plus HA electron beta. You will notice these functions are asymmetric as long as we stipulate that alpha is equal to minus beta. In the real world, it was found spectroscopically that the original function of subtracting hydrogen 1 from hydrogen 2 describes the ground state of the hydrogen molecule. The three possible asymmetric additions represent the triplet excited state spectroscopically. What triplet means is that there are three energetically identical, in other words degenerate, states generated. Additionally, through the application of Fermi-Dirac statistics, it was found that alpha is equal to plus 1/2 and beta is equal to minus 1/2. Your familiar M sub S values. So to conclude, when we look at molecules and spin, we find out the following. Three quantum numbers are derived from what are known as ab initio calculations. N, the principal quantum number, is the energy level as any positive integer. L, the angular momentum quantum number, is the orbit. You can have any integer from 0 to n minus 1. M sub L, actually M sub LZ, is the magnetic quantum number. It gives the direction of the orbit relative to the z-axis and can have any integer from minus L to positive L. The fourth quantum number is derived from general relativity. M sub S, the spin quantum number, can have possible values of plus 1/2 or minus 1/2. Particles with a spin of 1/2 are called fermions. They obey Fermi-Dirac statistics. Fermions include protons, neutrons, and electrons. The Pauli exclusion principle, that a wave function must be asymmetric with respect to exchange of variables, therefore translates to no two particles can have the same four quantum numbers. This is because, since spin only has two values, there can only be two electrons per orbital. You get identical results for atomic or molecular orbitals. The important takeaway from this is that you already knew the answer from freshman chemistry. Trust the answers that you already know. They will carry through the rest of the course. And always trust in yourself.